Right. Hi, everyone. Welcome to class. Okay, so we're moving to another session today. Pretty much we're looking at 11.10. Okay, so we're closely wrapping out on completing the class as the semester comes to an end. Okay, so 11.10, we're really going to be studying Taylor and Maclaurin series. Okay, so the Maclaurin series is actually a special type of the Taylor series. And Taylor series has very wide applications in different fields. All right. So far, what have we seen? So let me just write as a means of little introduction. Let me just write that we have seen power series. We have seen power series representation of certain specific functions. Okay, so we really want to make progress by now studying Taylor series and Maclaurin series, right? Our goal in series. Okay, so I want you guys to follow me closely because I don't want to lose anybody as I teach and as I explain some of these concepts. Now, suppose we have a function. So let f be any function that can be represented by a power series. Now, but in this case, we want the power series to be centered at a certain number. Let's call it A. If I give you a function that can be represented by a power series centered at A, what does that mean? It means that I can write a function f of x as c0 plus c1 x minus a. Remember, this is the center, right? Plus c2 x minus a all squared, right? Plus c3 x minus a cubed, on and on. We saw this from 11.9, and we know that x minus a is going to be less than my radius of convergence. Okay. Now, what happens if we replace x by a certain by a? Okay. If we replace x by a, what happens? We're only going to be left with the constant term. Okay, keep that in mind. If I do some certain replacement by saying let x equals a, then if you plug in x equals a in equation 1, what happens? You're only going to be left with a constant c0. Now, in 11.9, we looked at term by term differentiation, right? Okay. Now, from 11.9, we saw that we can differentiate the series term by term. Okay, if you miss out on that video, I want to encourage you to go back and look at that video. Now, if we do that term by term, that means from equation 1, I can actually find the derivative. Okay, so f prime of x, differentiate equation 1 with respect to x. You will have a c1 here plus 2c2 x minus a plus 3 C3 x minus a squared. And of course, I can keep going on and on. Now, again, also my x minus a is less than my radius of convergence. Now, the same thing, if I do the same kind of replacement, if x equals a, what happens? I'm only going to be left with f prime of a equals what, guys? C1. So that means, again, in equation 2, if you do replacement by plugging in x equals a in equation 2, you will only get the constant. All right? So we can keep doing this same thing on and on and on, okay? And then we can see what happens. All right, so number 3. In number 3, let us even differentiate equation 2 again, okay? If I differentiate equation 2 one more time, what happens? This becomes 2c2 plus, this is going to be 2 times 3, c3x minus a. Now, remember, keep in mind that there's another term here, which is going to be like, over here, we're going to have a term that's going to be 4c4, right? X minus a cubed. So if you differentiate that guy, you would have a 3 times 4 c4 x minus a squared. I mean, this can continue going on and on. Now, if I do the same thing again, if I let x equals a, what happens? My f prime prime of a is going to be 2c2. Now, that means each time I keep letting x equals a, I'm only going to end up with a constant. All right? So let's say number 4. If I even differentiate equation 3 one more time, so that means I now have the third derivative, right? This is going to be a 2. All right, so times 3c3 plus 2 times 3 times 4x minus a plus, you're going to have 3 times 4 times 5 c5x minus a squared. This can continue. I can continue doing this forever, okay? This is a times. And then, of course, again, this guy is less than r. The same thing I have been doing, if I continue to make that substitution, let x equals a, what happens? My f prime, third derivative of f, when you plug in a, you're just going to have that constant, 2 times 3c3. Now, what is 2 times 3? That is 6, right? In terms of factorial, 6 is just 3 factorial. Okay, so this is like 3 factorial equals to 3 times 2 times 1, which is still 6, okay? Now, you will see in a minute why we really want to just put it in terms of the factorial as we did, all right? If I wanted to write this guy, 2c2 in terms of factorial, I could have just done 2 factorial c2. Now, we begin to see that there's a pattern, right? F prime of a gave us c1. Now, from equation 3, f prime prime of a gave us 2 factorial c2. Now, go to equation 4. F prime 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 of a gave us 3 factorial c3. Now, you begin to see that as we keep doing that, it keeps, we see that there's going to be a pattern. If we go to the next one, the fourth derivative with respect to a is just going to give us 4 factorial c4, 5 factorial c5, and on. Okay, so now let me say by now, we can see the pattern. Okay, so I'm just trying to explain very slowly, taking it from the basis, so that when we start applying some of these things, it can be easy to follow. We see the pattern. If we continue to differentiate and substitute x equals a, what happens? We obtain f, we have n of a. Now, what does this guy mean? I'm going to tell you that in a second. So if we continue, this is what we're going to achieve. Okay, and I can write this guy in terms of factorial. This is n factorial Cn. Now, this guy on my left hand, this guy is the nth derivative of f. Evaluated cos. Now, if my n is 2, remember, if you have 2 here, this just means second derivative, okay? This guy is going to tell me about second derivative. If my n is 3, it tells me third derivative. If n is a 4, fourth derivative. Okay, so keep that in mind. Now, you see from this equation, let me call this one equation star. Okay, so from equation star, what do I know from equation star? I see that this guy equals n factorial Cn. Those Cn's are actually constant, right? Remember we saw C2, C3, C1, and the likes. Now, I need to make Cn the subject of the formula. So what do? Divide through by n factorial. So that means my Cn is going to be this guy. Okay, so now, so far, what are we trying to do? This is going to lead us to a theorem, which, tells us about that gives us an idea of what the Taylor series is all about. Okay, so it's really going to give us that, and we'll see what's happening. Okay. Now, this formula, keep in mind, guys, that this formula holds even when n is 0. Okay, n can be 0, n can even be from 0, 1, 2, on and on. Why? Because 0 factorial is just 1. And you may also have a question like, okay, what is f of 0? F of 0 means that do not differentiate, okay? Do not take any derivative. So keep that in mind. When you have f of 0, do not differentiate. F of 0 is just the original function. Okay, so when you have f of 0, we're really talking about the original function itself. Okay? Now, theorem. Now, if f, okay, has a power, if we have a function that has a power series representation, so at the level of this theorem, we want to put things together, okay? If f has a power series representation, now sometimes if we don't use the word representation, we can use the word expansion, all right? So those words can be used interchangeably. If f has a power series representation at A, okay, so what does that mean? That means we are saying that if f of x can be written as this. Okay, so that's what it means to have a power series representation at A, where this guy is less than R. Now, if a function has a power series representation at A, now then its coefficients are actually going to be given by the formula Cn equals this guy. Now, your n is free to start from 0, okay? 0, on and on, not a negative number. Now, if you look at this guy right on top, and that's what we really proved, right? And this is it put together in a theorem. If I have a function that has a power series representation, what does that mean? It means I can write a function like this guy in the box. Okay, now, but the thing is, how can I find these coefficients? The Cn are the coefficients. How can I find them? Then you use this formula. Okay, this guy tells you about the coefficients involved in the power series expansion. Now, having said this, we are good to make a definition about the Taylor series definition. So, and here we want to define the Taylor series of the function f at a. If you don't want to use the word at a, you can use about a, or centered at a. Okay, so I can use this guy. You can just use about a or centered at a. Okay, those can be used interchangeably. Okay, so any power series of the form f of x equals, you got a sigma notation, this is this guy, divided by, this is the form x minus a to the power of n. Okay, this guy is a Taylor series expansion. Okay, now if you don't like it in terms of the sigma notation, let's split things out. That means this is f of a plus f prime of a divided by 1 factorial x minus a. When n is 2, what happens? You have f prime prime of a divided by 2 factorial x minus a squared, and I can keep going, right? Any power series of this form is actually called the Taylor series of the function at a. Now, if you're being asked, oh, given a function f, what is the Taylor series of the function at a? Then you are talking about this guy in box. Okay? Now, but remember, when we started, I told you guys that the Maclaurin series is a special type of the Taylor series. So let me come here and do this guy, just the Maclaurin series. Okay, so the Maclaurin series is a special type of Taylor series. Okay, zero. Now, if you have a Taylor series, the moment your a equals, let's go this. Now, just set your a to be 0. What happens? So that is, we're talking about f of x equals, you got this guy. Remember, your a is 0, right? So you have fn of 0 divided by n factorial. That was formerly x minus a to the power of n, right? But this a is 0. So when you do x minus 0, it gives you x. So that means you just have x to the n. Now, if you want to spread things out in this case, you have a f0. When n is 0 plus 0, you have f0 divided by 0 factorial, which is 1. So you don't have to bother about this part because 0 factorial is 1, plus f, which is 1, okay, f prime of 0 divided, divided by 1 factorial. You do have a x plus f prime prime of 0, x squared divided by 2 factorial. This can and on. This is exactly what we call a Maclaurin series. This is exactly what we call a Maclaurin series. Okay, so this guy, what we call Maclaurin series. Okay, I hope you get the difference. Maclaurin series is a special type of Taylor series. However, that means that your A has to be 0 for Maclaurin series. This guy here is a Taylor series. Okay, but of course, it's a Taylor series of the function at A. This guy is like Taylor series of the function at A equals 0. So that's why we call it the Maclaurin series. It's special. Now, let's begin to see how this can really be applied, okay? Let's see how these formulas can really be applied. Okay, so example. Now, we want to find example. We want to find the Taylor series expansion for a polynomial at A equals -1. Okay, solution. Now, can I remind you guys that recall that for Taylor series at x equals A, f of x is given by this series. This is A n factorial x minus A n, right? And this guy is really what we call the Taylor series at x equals A, right? Now, but in this case, now my A is -1. So that means I'm interested in when this guy here is -1 and when this guy here is a -1. Okay, so that's really my interest. All right, so let's get started. Now, I'm going to show you guys a very, a tabular form, which really makes life easy. Okay, so to put up a table. Now, remember, this guy goes from 0 to infinity. You cannot do infinity, right? You don't want to go from 1 to 1 billion. I mean, there's not going to be an end. So if you're using this table format, you can just pick some numbers, okay? Like 0, 1, 2, 3, and let me just stop at 4 for the sake of, going a little bit distance. All right? So then you have Fn of this guy, Fn of x. However, my main interest is when you evaluate this guy at the A, okay? But what is the A in this case? -1. Okay, now, so how do I know that this is the table I need? Remember, we can spread this guy out. You have f of x equals f of A. I mean, I think we have that from here. Can you see this guy? This part. So that's what we really want to write back here. F prime of A divided by 1 factorial x minus A plus f prime prime of A x minus A divided by 2 factorial. I can keep going on and on. Okay, so this is what I'm trying to evaluate because these guys are numbers, right? This guy's a number. You are evaluating as a constant. This guy's a number, and this guy's a number, right? So can you see why we need them? All right. So what is f of x? Remember, f of x itself is just s cubed. Right? Now, when n is 0, remember that is when you don't want to do anything. That means that's the original function. F of 0 of x is just the original function, which is s cubed. Okay? So that means over here, I'm going to have a s cubed. Now, when n is 1, that means differentiate x cubed once. So that's going to be 3x squared. When n is 2, differentiate this guy, you have a 6x. When n is 3, differentiate this guy, you have a 6. So many a times when you know when to stop is when you have a 0. If you differentiate this guy, it knocks it off, so you just have a 0. Okay? But again, there are some functions that would not, when you like for instance, the exponential function, if you keep differentiating, it never goes to 0. Okay, so you always have to keep that in mind. Like the logarithmic function ln of x never goes to 0. So you need to think about all of those two. So it's not just about when it goes to 0. Okay. All right. So continue to make progress. Remember, where did we start from? When n is 0, that means you're not doing anything to the function. That's just the original function, and that's what I have here. When n is 1, f1 of x means differentiate the function once. This is this guy. When n is 2, differentiate it twice. But with respect to this table, once you put in x cubed here, 1 means differentiate once, right? And you have this guy. At the level of 2, differentiate what you have in 1. At the level of 3, differentiate what you have in 2. At the level of n equals 4, differentiate what you have in 3. So now this next step, what is this next step saying? Plug in, this is fn of x, right? What is fn of -1? When x equals -1, what happens? You got a -1 cube, which is what? -1. This is going to be 3 times -1 squared, and this is just 3. This is 6 times -1, which is -6. This is 6, and this is 0. Okay. Now, so you see what we're doing. So f of x, a equals -1, right? So this place we have f of -1 plus, what is f prime of 1? F prime of negative, okay, so let me not skip step, guys. I meant f prime of -1, not 1. So this is x minus 1, right? Plus f prime prime of -1 divided by 2 factorial x -1 all squared plus f prime prime -1 divided by 3 factorial. This is x minus 1 squared, right? All right. So that's a good place to stop. If you get to f of 4 is already 0, so I don't want to think about that one. Now, what is f of x? What is f of -1? Let's go back. What is my f of x? F of x is x cubed. Now, plug in x equals -1, you have -1. So this guy is -1. Plus, now let's go back. Okay, let me use a red pen here so that you guys can see what is going on. This guy is my f prime of -1. Over here, this is my f prime prime of -1. This guy is my f prime 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 of -1. And this guy is like my f4 of -1. So you see f prime of -1 is 3, right? This is a 3 here. 1 factorial is still 1. So you have a x plus 2. X plus 1, I'm sorry. Because negative times negative gives us positive. Plus, what is f prime prime of -1? F prime prime of -1 is -6. I'm going to come right here and put -6. 2 factorial is 2. Then you do have a x plus 1 squared. Plus, what is f prime 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 of -1? That guy is 6. So I'm going to come right here and put a 6 divided by 3 factorial x plus 1 cube. This should be a cube, guys. Sorry about that. This should be a cube. Okay. So this is f of x equals -1 plus, this is 3x plus 1. Now, these 2 takes off this guy, you have a 3 minus 3x plus 1 all squared plus, now 3 factorial is 6. 3 times 2 times 1, and that is just 6. You have this guy will knock off this guy. So I have x plus 1 q. Okay. So this is very easy. At this point, this is good. We're good with this guy. All right. Are we making progress? All right. Let's continue. Now, in the next example, I'm going to go a step further and write a closed form of this sort of Taylor series. If you have a Taylor series, in the next example, I'm going to show you the closed form. What do I mean by closed form? I want to write it in terms of the sigma notation, okay? So I want to make it nice and clean by writing in terms of the sigma notation, okay? We will see that in a bit. Now let's do another thing on Taylor series. Okay, so another example. Find the Taylor series expansion for f of x equals, now this is an exponential function, at a equals 2. Where do we start from? Okay, so we need to remind ourselves what the Taylor series formula looks like. So you have a fn of a divided by n factorial x minus a to the power of n. Okay. Okay. All right. So what do we do in this case? I know that my f of x equals e to the x and my a is 2. Now, but the exponential function is special. If you keep differentiating e to the power of x, it's really going to be the same thing. Okay, so this is what we do. So what is going to be f of n 2? Now that means I'm interested in this guy now. When my a is 2, right? Now, because I know the exponential function is never going to change. Okay, let me start from here. If I differentiate it many times, it's still going to be the same thing. So what is going to be fn of 2? E squared. So now what is going to be my Taylor series expansion? Let me go a little bit up. My Taylor series, I know this guy already. I know my A. This is N. I know my A. I know my N. Okay. My N is unknown. I mean, my N goes from 1 on and on. Okay. My f of x is going to be the sigma notation n from 0 to infinity. Keep in mind that this is what we're trying to do. X minus a. Now, do you agree with me that we already found this guy, fn of 2, and that's just e squared divided by n factorial x minus 2 to the n. So what is the Taylor series expansion of e to the x? It is just this guy. So this guy is what we call a closed form solution, okay? Or a closed form expression, as the case may be. This is the closed form. All right. Now let's do something with Maclaurin series. Okay, let's really do something with Maclaurin series. Example, find the for sine x. A0, okay? A is just 0. So the solution. Now, let's remember, how do we write Maclaurin series? F of x is the sum fn of 0 divided by n factorial, then you have x to the n. Now, I'm given that my f of x is really sine of x. Now, I gotta make life easy. I try to use the table, okay? So this is n. This is derivative, and this is where you evaluate. I gotta spread things out to remember that f of x is gonna be f of 0 plus f prime of 0 divided by 1 factorial x plus f prime prime of 0, you got a s squared over 2 factorial plus f cube of 0, f 3 prime, not cube. Okay, this is s cube. You can continue on and on. Okay, so now this helps us to know what we're really interested in. This is when n is 0. This is when n is 1. This is when n is 2. This is when n is 3. Okay, so I mean, these functions that do not terminate, I can just stop at 3. Okay, and if you have time, you can still go to 4. Now, when n is 0, that means do not differentiate. Okay, so that means this guy is original function. Okay. What is sine of 0? Sine of 0 is 0. Okay. When n is 1, that means differentiate what you have at step 0. If you differentiate sine, you have a cosine of x. What is cosine of 0? 1. Now, when n is 2, differentiate what you have at step 1. You have a negative sine of x. What is the negative sine of 0? 0. Okay. So when n is 3, you differentiate what you have in step 2. You would even have negative cosine of x. What is negative cosine of 0? Negative 1. But keep in mind that these guys, when we do the original function, no derivative, right? Let me just write no differentiation. And that's here, right? Here is where you have f prime of 0. Here is where you have f prime prime of 0. Here's where you have f prime prime of 0. The list is endless. I can continue, right? So let me just put dots to show that it does really extend. So now we need to plug in things. Okay, so no differentiation, and that is this part we have f of 0. Let me use my red. Okay, so I need to write it. I need to plug things back to this guy. Okay, this f of x, this one. F of 0 is 0, so I have a 0 here. F prime of 0. What's f prime of 0? It's 1. So you have 1 divided by 1 factorial. That's still a 1. So you have x. So if you keep doing that, you would have a s cubed over 3 factorial. In fact, I can tell you some of the next terms for free. Okay, although we didn't go far, but I can tell you the next terms. It continues on and on. Now, I need a closed form expression for this guy. Now, again, what's the closed form expression? I need to write it in terms of the sigma notation. Okay. Now, how do I build that? Keep in mind, you start with your sigma notation. Now you look at the trend. You see that the signs are alternating, plus, minus, plus, minus. So I know that I have a -1 to some, right? It can be n, it can be n-1, but I need to know what it is really. Okay. Now when n is 0, suppose this is just n, right? Okay. So when n is 0, you have 1. When n is 1, you have a -1, right? When n is 2, you have +1, and that keeps going. Okay. So this is fine. Now look at the x's and look at the numerator. This is x to the power of 1, right? X cubed, x to the 5th power, negative x to the 7th power, on and on. This is going to be x. Now you see they are odd. You have a 1, 3, 5, 7. The next thing is going to be a 9. So that means this guy is going to be 2n plus 1. When n is 0, we're going to plug things in and you see if we're really correct, okay? Divided by, look at the bottom too, the same thing, 2n plus 1, but in this case you have a factorial. So it takes a little bit of practice to be able to build a closed form solution. Some of the closed form solutions are really straightforward, but other times you really need to do some kind of thinking, okay? And how do you do that? You look at, if you have rational functions, you look at the behavior of what is going on the top and on the bottom. So think about when we study sequences and we're building the general terms for sequences. Now let's see if we are correct. So let me call it check. When n is 0, what happens? Plug in 0 here. And okay, so check, when n is 0, you have a -1 to the 0. Because this is a series, I need to sum things up. X to the 1 over 1 factorial plus, when n is 1, this is going to be -1 to the 1, right? And this is going to be like x. This is going to be a squared. It's going to be a cube, I mean. 2 times 1 is 2 plus 1, 3, divided by 3 factorial. When n is 2, it's going to be -1 squared, x to the 5th power divided by 5 factorial plus -1. When n is 3, this is going to be this guy. Interesting. Here is when n is 0. Here is when n is 1. Here is when n is 2. Here is when n is 3. Now let's see. So let me check. So my f of x is going to be x minus s cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, on and on. Okay, this just. So whenever you do your closed form solution, you always need to ensure that your closed form solution is correct. You always need to ensure that your closed form solution is actually correct. All right. Now, the same way, this is for sine, right? So you can also do the Maclaurin series for cosine, actually. Okay, keep that in mind. Let's look at another example. Find the Maclaurin series. Now, we're going to step it higher in this case now. For the function, let's pick the exponential function, okay? And its radius of convergence. Now, that's where we're stepping it higher a little bit. solution. Now, where do you start from? You recall, now we're working with Maclaurin series, right? So I need to recall the formula for the Maclaurin series. Recall that f of x equals, has to be a 0 divided by n factorial x to the n. This is just the Maclaurin series. Okay, let me go back here and remind you guys, this guy is the Maclaurin series. Okay. All right, so similar to what we did before, I know my f of x is e to the x. This is an exponential function. It's never going to change. It's going to be the same. So that means if I differentiate this guy nth times, you have the same thing. But I'm interested in fn of 0. So e to the 0 is just what? 1. Amazing. So what is my f of x going to be? The sum from 0 to infinity. Fn of 0 is already 1. So I just have a 1 over n factorial times x to the n. So which I can just write, of course, as s to the n over n factorial. So the Maclaurin series we really want is this guy. And if you even want to express this guy, if you want to split things out, this is what you expect. As you go from 0 to on and on. But that's the first part of the question though. We're not done, okay? So now we want to find the radius of convergence. Now, to find the radius of convergence. You remember from 11.8, when we studied power series, we used the ratio test, okay? So use ratio test. Okay, so my AN, I need my AN. Now, so look at this guy. What is my AN? My AN is this guy, right? X to the n divided by n factorial. What is my a sub n plus 1? This is going to be x to the n plus 1 divided by n plus 1 factorial. Now, because I want to do Taylor series, I like to first simplify my a sub n plus 1 so that life becomes so easy for me, okay? X to the n times x, and you do this by indices. Now, we have seen this before, okay? I showed you guys this before, how to deal with factorial. Okay, so perhaps let me just do a little reminder here. When you have n factorial, that means n factorial is the same thing as n times, keep decreasing by 1 as you go on and on until you get to 1. Now, but I can choose to stop at n minus 1. If I'm going to stop at n minus 1, I'm going to put a factorial symbol here. Now, but this is n plus 1 that we're dealing with right now, right? N plus 1 factorial. Remember, it's going to be n plus 1. The next guy is going to be n plus 1 minus 1, and that's n. So if I want to stop at n, I just put the factorial. Okay? All right, so ratio test, limit as n goes large, a sub n plus 1 divided by a sub n. Limit as n goes large. What is my a sub n plus 1? So let me just put that guy there carefully, okay? Now, but a sub n is a rational function. So by the time you put it in, it flips. N factorial divided by x sub n. This guy cancels this guy. Remember, when you do ratio test, some things cancels out, okay? Yeah, or perhaps I say you get a simplified form. Goes large. This is x divided by n plus 1. Now, but obviously I can pull out my x, so I have an x here. Limit as n goes large, 1 over n plus 1. Now, but if you, of course, I don't even need this absolute value right now because n is positive. What is this limit? This limit is 0. Okay. So that means my L in this case is 0. And of course, 0 is less than 1. So that means this guy, by ratio test, converges, right? So, and when L is 0, remember that we studied this in 11.8. That means my radius of convergence is infinity. Okay. And if this is infinity, the interval of convergence is negative infinity to infinity. Okay. So when you have infinity, you don't test endpoints, right? When you have infinity, because you cannot plug in infinity, it will make no sense. All right. Does this make sense? So remember, we're kind of doing, again, as I always mention, this class is progressive. We keep going, we keep building. We really need to rely on our previous ideas, previous knowledge, the things we've studied previously to really help us to achieve what we need to achieve. Okay? Now, let me tell you guys that there are some very important Maclaurin series. So okay, so let me call them important Maclaurin series. Now, the one we've seen before is this guy. I mean, by now, if you close your eyes, I hope you can write a closed form expression for this guy. Oh, this is excellent. And if I even want to write this guy out as a sum, and the radius of convergence here is 1. We've seen e to the x. Okay, e to the x, we did this as a matter of fact as an example. If I need to write this guy as a sum, this is what I really have. And my r is infinity. We saw that. Now we've also done something with respect to sign. X 2n plus 1 over 2n plus 1. This is like a summary actually, okay? Putting these things together for you. X minus s cubed over 3 factorial plus x to the 5th over 5 factorial minus over 7 factorial, on and on. And my radius of convergence is actually infinity. Now, what about cosine? Okay, so we really have something also to work with in terms of cosine. N from 0 to infinity. Negative 1 to the x to the 2n divided by 2n factorial. Okay, I know we didn't do cosine, but the same principle works, and these are kind of famous ones. Okay, the radius of convergence is also infinity. Now, you also have for tan inverse of x, arctan of x. For arctan of x, this is the closed form expression. Okay, x minus x cubed over 3. Now, the one for tan inverse of x is similar to sine of x. The only difference is that for sine, you have a factorial on the bottom. For tan, you don't have a factorial. But the radius of convergence is 1. Okay, so these are kind of important ones which are good to talk about, good, or perhaps let me say good to, point out to you for you to really see them. Okay. So now let me talk about multiplication, and division of power series. Now, just like polynomials, you can actually add or subtract power series. Okay, so power series can be added and subtracted like polynomials. Okay, they can also be multiplied and divided like polynomials. Okay, now but you need to note that when we do this, we can only find few terms. I mean, these are infinite. We're talking about a power series with infinite terms. So, I mean, we can't keep doing that forever. So we only note we find only first few terms. I mean, because it's infinite. I mean, we can never do that forever. Since the initial terms are the most important ones. Okay, example. Find the first three non-zero terms in the Maclaurin series for e to the x sine of x. Okay, so we need to find the first three non-zero terms. Solution. Okay, so now we really need to make life easy and we need to work smart. Okay, so what would this entail if we do work smart and then try to put things in perspective? What are we going to do? Okay, so this is exactly what we're going to do. Now, if I take you back a second to the summary table, which we had, we know the Maclaurin series expansion for e to the x already, okay, which is this guy. We know the Maclaurin series expansion for an x already. So we need to work smart. You don't have to go to do it from the scratch. So that means e to the x sine x. What is the Maclaurin series of e to the x? It's 1 plus x squared over 2 plus x cubed over 6. Now remember, it's 2 factorial and 3 factorial, but because I need them, I just need to convert them. I need to multiply things out. What about sine? You have x minus s cubed over 6. Now, what do? You multiply this guy out. Now, if you keep doing that, you're going to end up with x plus x squared plus x cubed over 2 minus s cubed over 6, on and on. It goes like forever. So at the end of the day, e to the x, this Maclaurin series, is x plus x squared plus x cubed over 3, on and on. Okay, I hope this makes sense. Okay. Now, another example, find the first three non-zero terms in the Maclaurin series for tan x. Now here we really need to work smart too, okay? So what is tan x? Tan x is sine over cosine, okay? But we do know the Maclaurin series for sine already. It is x minus s cubed over 6 plus x to the 5th over 120, on and on. Then you divide the whole bunch by the Maclaurin series for cosine. Okay, let's flip back a little bit. This is 1 minus s squared over 2 plus x to the 4th over 24. I can keep going. Okay, so how do you divide these guys? We really have to go back to long division. Okay, so that is us trying to do this is x, okay, minus 1 over 6 x cubed plus 1 over 120 x to the 5th, on and on. Here you have a 1 minus 1 over 2 x squared plus 1 over 24 x to the 4th, on and on. Now, I'm not going to go into a lot of details because these guys are pretty much standard. You have Maclaurin series for tan x, they are popular or famous as it were. But when you do the division, you're really going to have, okay, it's going to be this guy on the top, 15 x to the 5th, x minus 1 half, I mean, this is a cube, plus 1 over 24 x to the 5th. I need to get rid of x, I subtract. I'm going to left with x, this guy. Okay, so I'm just going to tell you guys what they are really going to be. I want to get rid of these guys, they are the same. So this is 2 over 15 x to the 5th. Okay, so I mean, I will keep doing that, but it's endless. So I better stop somewhere. See, this guy is just, okay. Makes sense, guys. So yeah, it's possible to multiply. It's possible, I mean, to divide as well. Those things are pretty much very possible. Very, very possible. And then we can work with them in that manner. Okay. So I hope it all makes sense. Trying to understand. I mean, I try to put it out here in like a very simplified form, and in a way that you guys can really get it, because these concepts are a little bit technical but not difficult. Okay, and there's a higher expectations about them. They're very very powerful tools that you need. Okay, you might need them for your research at some point, or maybe your your research, or maybe you're doing a project or something. Okay, all right.